In this video, we're going to do a little recap of Newton's third law. And as you probably know, Newton's third law says that for every action, there's an equal and opposite reaction. Sometimes we might say for every force, there's an equal and opposite force. And what we'll see in these video clips is kind of two things. One, at the top, there's going to be two carts, a red cart and a blue cart. They're smart carts from Pasco Scientific. They're going to interact with each other with the force sensors facing each other, and in the bottom we'll see a graph of the force measured by each of those force sensors. So we'll kind of see the interaction between the carts and measure the forces that they experience during that interaction. And in the first one, I just took the carts and I pushed them against each other. So sometimes they're moving, sometimes they're stationary, but as you can see, it doesn't really matter what the carts are doing. Anytime they're in contact with each other, they're both measuring the exact same force in opposite directions. When they separate, the force goes to zero because there's no more interaction, but it doesn't matter if they're moving, stationary, moving one way or the other, tap into each other really quickly. They both measure the exact same force in opposite directions. So that's kind of a clean example of Newton's third law. A little less clean when things are moving, not being pushed directly. So in this case, we have the red cart and the blue cart. They're going to start at opposite ends of the track and they're going to be pushed toward each other. So we'll only get a momentary force when they're in contact with each other. But what we'll see is that that force is both equal and opposite. So each cart experienced the same force in opposite directions. So that's the force, the equal and opposite force, but you can also see that that reaction is equal and opposite. Both carts were moving toward each other. When they bounced off of each other, they moved away from each other pretty close to the same speed. So the force was equal and opposite, and their reaction to that force was also equal and opposite. It's not always going to be that clear though. So let's look at another example of a collision. And in this case, we have the red cart and the blue cart. The red cart's going to be pushed. It's going to collide with the blue cart. The blue cart, you can see, has some masses added to it. So again, we'll get a readout of the force graph. And when they collide, you can see that they both experience the same force in opposite directions, but that reaction was different. It was not equal. It was opposite. One cart went to the left, the one went to the right. So they went in opposite directions, but they both went in different velocities. This is because mass affects how an object reacts to force. So forces, unbalanced forces, cause acceleration. An object with more mass is going to have less acceleration for the same force. So even though these two carts experienced the same force, because their masses were different, their reaction to that force was different. And then one final example of this, and I apologize, I did not set this video up, so I had to find one off of YouTube so we can watch this physics teacher's setup. And what we have are two, maybe not so smart carts. They are touching each other with a compressed spring between them. And what this physics teacher is going to do is release that spring. It will push on both carts with the exact same amount of force. So both carts will experience that equal and opposite force. But you can see the cart on the right has some masses added to it. So its reaction to that force will not appear to be equal. So opposite directions, but not equal. So let's go ahead and take a look at that. So just to wrap things up with this video, Newton's third law says for every action there's an equal but opposite reaction. Another way to say it is for every force there's an equal and opposite force. And we can see that, we can measure that force. We can really see quantitatively that that force is both equal and opposite. But when we watch things interact with each other, their reaction to the force is not equal. It's opposite, but it's not equal because different masses will affect how things react to force. So just to recap Newton's third law, when two objects interact with each other, they both experience the same force in opposite directions. If their mass is the same, the acceleration will be the same. In other words, their reaction to the force will be the same. If their masses are different, their accelerations will be different, which makes their reaction to the force appear to be different. However, if we analyze the situation, we can see that if the force each experiences is the same, then mass times acceleration for each cart will be the same. And we can replace acceleration with change in velocity over time. And since both carts experience the same force for the same amount of time, we can divide out that value. And this leaves us with mass times change in velocity for the red cart equals mass times change in velocity for the blue cart. And since in this case both initial velocities were 0, this becomes mass times velocity. So if we go back to Newton's third law, the velocity each one has is not equal and opposite, but mass times velocity is. Because of this, we have a measurement that includes both mass and velocity, which we call momentum. A few details about momentum. We use the symbol P. P equals mass times velocity. Momentum is a vector, which means it has magnitude and direction. Positive and negatives in this case would indicate direction, not more or less momentum. Also, momentum can be at an angle that can be broken into x and y components, just like we've done with velocity and force and things like that. One important characteristic about momentum is that in a closed system where there are no outside forces, momentum is conserved. Whatever momentum there was before the interaction, there's the same amount after. Different objects may have more or less momentum, but the total amount in the system stays the same. If we think about the car example, when they were at rest before they separated, the momentum of the system was 0. After they push apart, the momentum to the left equals the momentum to the right, and since one of these is in the negative direction, the total momentum still equals 0. So now what you're going to see is some video clips of smart carts interacting in different ways, and we want to analyze these in terms of conservation of momentum. So at the top of the screen, you'll see a clip of the smart carts that'll roll down the tracks. Sometimes one will be moving, one will be stationary. They'll have different combinations of mass. And then at the bottom of the screen is a little table that indicates the mass and velocity and momentum of each one before and after the collision. I just made up some simple numbers, masses of 1, 2, or 4, and velocities kind of along the same lines, just so we can have some easy calculations. But what I want you to pay attention to is what is the momentum before, and then what's the momentum after, and then think about the way the force, so when they interact, each one experiences this as the same force. The red cart applies a force to the blue cart. The blue cart experiences the same force back to the red cart, and it's through that force, that interaction, that the momentum gets transferred between the carts, but the total amount stays the same. So you might have to back up and watch them again, but just pay attention, look at the situation before they interact, and then the situation after they interact. So what we saw in each of these is that the total amount of momentum before they interacted stayed the same when you think about the momentum after they interacted. When we get back to school, we'll do a lab where we look at this a little closer and we kind of prove this. But for now, whenever we look at things that are interacting, what we're going to do is we're going to calculate the momentum before they interact and use that value to predict some things that are going to be the case after they interact. So we'll look at some sample problems now to see this in kind of a different light. So in this situation, we have a person standing on a skateboard and they are holding a bowling ball. So the person has a mass of 55 kilograms. The bowling ball has a mass of 4 kilograms and they are initially at rest. So that means if their velocity is 0, the initial momentum in this situation is also 0. So then the person throws the bowling ball to the right at 18 meters per second. And in order for momentum to be conserved, that means the person is going to move to the left. So we have momentum to the right. We have to have momentum to the left in order to conserve momentum. And we want to know how fast is that person going to move to the left. Well, conservation of momentum tells us that the final momentum must be equal to 0. And that means that m times v for the person, so 55 kilograms times their velocity, plus m times v for the bowling ball has to equal 0. And so if we solve this, that's 55v plus 72. And that's going to be negative 55v equals 72, which means the velocity of the person is going to be 72 divided by negative 55, or negative 1.3 meters per second. And the negative sign just indicates that the person is moving to the left. So you could say their velocity is negative 1.3 meters per second, or their velocity is 1.3 meters per second to the left. Either one of those would be fine. And I have a tendency to not write down units when we solve problems, but just to sort of make sure we're clear on that, that 72, that's the momentum. That was m times v. So if we were including units, that would be 72 kilogram times meters per second. That would be the units for momentum. So in the second question, we have a collision. So we have this lump of clay and a basketball. I'm going to shade that in orange. All right, so the lump of clay is initially moving at 9 meters per second to the right, and the basketball is moving at 12 meters per second to the left. The basketball has a mass of 0.5 kilograms, and the lump of clay has a mass of 1.5 kilograms. Okay, and afterwards, they're going to stick together. So there's our basketball, and now there's the lump of clay stuck to the side of the basketball. And we want to know, now they're combined into one mass, and we want to know what is their velocity together after that collision. So again, we're looking at this in terms of momentum. So the momentum of the clay, if we just look at the clay on its own, I'm going to say to the right is positive. So we say m times v, so that's 1.5 kilograms times 9 meters per second. So the lump of clay has a momentum of 0.5 times, 13.5 kilogram times meters per second. The basketball has a momentum of 0.5 kilograms times 12 meters per second. So that works out to be 6. And should have put in a negative sign. It's moving in the negative direction. So that means the basketball has a momentum of negative 6 kilograms times meters per second. So our total momentum initially is going to be those two combined, 13.5 plus negative 6. So our momentum before the collision is 7.5 kilograms times meters per second. And that is momentum to the right. And so just based on the direction of momentum, that means after this collision, they must together be moving to the right. Before they collided, our total momentum was to the right. So afterwards, we still have to have a total momentum to the right. As to how fast they're going, we know our final momentum still has to equal 7.5 kilograms times meters per second. That's equal to m times v. Well, now they're combined into one mass. So that's our 1.5 kilogram lump of clay plus a 0.5 kilogram basketball times their velocity. And so that's going to be 7.5 equals 2 times v. So our velocity in this case is going to be 3.75 meters per second. And that's came out to be a positive number. We already knew it was going to be to the right, but it's still going to be to the right. So hopefully that kind of gives you an idea. I am sure that there are going to be some questions about these, which is great. You can email me if you want to, or you can wait till, if we come back to school on Monday, and we can discuss some questions there. But hopefully this lays some groundwork that we can move forward with next week. I hope you have a great snow day and a great weekend, and I'll look forward to seeing everybody on Monday.